in this third part of this tutorial, we like now, after planning, now we have a circuit, okay, that we know very well how it works. So now the time that the idea is that simple. If we know already a circuit, let's develop it using the usual electronic design automation tools. So let's develop to synthesize a kind of an entity like a given gate structure, and then let's test it, that now you can simulate that architecture ideally. So it's going to be a functional simulation, or later on you can simulate it, in time to go and measure propagation times associated to a given technology. So once you have decided the target chip, you can also go and simulate the gate level, at this gate level, the circuit, and get, for example, the specific propagation time at a given transition of signals, or you can run the timing analyzer to get the worst case scenario, and from that measurement, from that parameter, obtain the maximum frequency of operation. How fast is indeed the circuit that you have invented? So that is the purpose of this third part on the RS latch design. So after having explained the specifications of the RS latch and going through the design of this device using, the concept of states and the concept of feedback wire to connect again the output as an input, and generating by means of the new truth table a given circuit like this based on NOR, now it's time for developing. So the basic idea here is that simple. Let's translate into a VHDL file this simple circuit, and then we can continue keeping an eye on the deduced or generated or synthesized circuit by the ADA tool. And finally, we can inspect as well the technology view and go to this testing section. And here we will pay attention to the test bench to get some results, right? So let's go. Because this is a tutorial, it is easy to find here the latch already solved. So let's save this file in the right folder. So save the link as, and this time is going to be in P5, and this is a new folder that we name RS latch. That's the name of the device, that's the name of the project folder. So now let's save that VHD in this folder, and this is simply a very simple circuit based on gates, so nothing else is required, no components or nothing else but this structure. So the idea is that this VHDL file contains the translated equations, that's simple, in the architecture. So now it's time for running, the Quartus Prime, and go through the starting a new project and the like. So the usual steps: File, New Project Wizard, Next, go to the right folder, this is L, CSD, P5 and RS latch. Let's take the name of the folder as well. And now let's name the project as RS latch PRJ, and the top entity in the VHDL file is RS latch. So next, empty project. Let's add this file to the structure and say next. Let's select the cyclone, for example, the cyclone available here for this Quartus Prime is up there in Intel devices. That one, for example. The Cyclone 4, or the Cyclone 4 is that one, for example. or the max 2, right? There is no problem. You can switch the device you like, so you can select it. So copy the file. So this is just to show you that we have different families of different logic devices, complex PLDs and FPGAs, and every one of them with its internal design and features. So let's select the max 2 and that one. So it is just like that. It appears on the list. It's available, so you say next. And now, as usual, the simulation tool is Model Sim Altera, and this is VHDL. You say next, finish. And now it's time for organizing the project and letting the system compile it. Okay, like this, synthesize all. So the synthesis process has finished, and what we've been synthesizing, as you see, is the entity. R and S are inputs, Q is the single output that you have here, and then the architecture is based on logic equations. You are writing here exactly the same signals that you have in your schema. So this is the simple, you see, this is the simple architecture, just 2 NORs and a buffer. That is what is in the circuit. That's simple. Let's see what happens now, keeping an eye on the netlist viewer, the RTL. So the RTL looks like this. You see, perhaps the gates has some differences, but pretty much everything is here. So that is the interpretation of the circuit that generated the Quartus prime. Well, it's quite easy to see that this circuit matches what we have in mind. And then perhaps you also have to keep an eye on the technology view, because this simple equation is solved, you see, in a single, just in a single memory cell. So that is the memory cell, the simple logic cell, not memory cell. Okay, so this is what you get when you synthesize that in a complex PLD or an FPGA. So now it's time for generating the test bench, right? Processing, start the test bench template writer. And now, if you like, you can go to the folder location, P5, latch, simulation, model sim, and take the RS latch template, Ctrl+C, and place it on the top folder, and change the folder extension, the file extension, VHD and RS latch test bench, that way. So now it's time for editing it, and Node Plus, it's the right editor. So you see, this is the libraries, the entity, the architecture with the input and output signals. Okay. All right. And then there is the component instantiation. You see, you have here kind of a component instantiation. So what we are translating now to VHDL in some way is that fixture, okay, the test bench fixture. So it is somewhere here in this tutorial, down there. Okay, this is the test bench fixture that we are translating now to VHDL. We have the unit and the test, that is that RS latch. We will watch results and analyze results in a waveform viewer. And now we will go and translate the input stimulus that are the ones, for example, represented in this picture from the specifications. So now our aim is to translate this stimulus into VHDL and place it down there in the process box that represents this idea of generating different ones and zeros to apply to the circuit. And additionally, we'll attach every time. Well, every time is just a multiple of the min pulse variable. So this is what we have in mind. So we will delete this init process and the always process as well. So here we have room to place our stimulus and our constant. So this is what we get from this web page. Okay, here you are, an example test bench already solved. So you can open it and copy what is necessary or what you think that may fit here. You see, you can copy that constant of 1 microsecond and a half. Just here. So min pulse is 1.5 microseconds, and this means, for example, this is the min pulse time width. So 1.5 microseconds means that we can run the simulation for example, 200 microseconds, and that's enough. And then here we can inspect the file and copy the stimulus process. That means applying values in R and S, Control C and paste, and that's it. You see, it doesn't have to be the same, but you get the idea of, you know, for example, starting with R and S not activated and then activating reset. So you see, this is what you like to do here, is to reset. You see, and this means that the system is yet here in an unknown state. That's the command that attached to this situation. Then you set and you reset, and then later you set signal, and you can repeat that process several times. Okay, that's the idea. You can also simulate, as you see here, impossible conditions. R is 1 and then S is 1. So you may expect here an impossible situation, so the output is not predicted, or something that you can attach to a given value. It may be unstable, the same way that you saw that in Proteus, that was an oscillating. But here in this simulator, who knows, perhaps you get a simple value as 1 and 0, but you know, you have to realize that this is an impossible situation. All right, so look at this. You set S, you set, this is set, okay, and then you are applying a reset pulse, and then you are applying a set pulse as well. So this is what makes it an impossible condition, and that is here for a while, right? For min pulse, for example, for 2.2. So then you get rid of the R, okay, later on, and so this is not impossible, but this means that the system will set Q equal 1. That's what is the system trying to do here, right? If you apply after deactivating the reset, okay, what is kept here is s equal 1. So the Q will be set high. This is like save 1, right? So this is the test, for example. Later you can restart the simulation process and get all the input vectors and try again with all the possible combinations of ones and zeros at the input. But that's okay for now. So let's save this file. And now you see in the folder you have the basic architecture and the test bench. So now it's time for launching from the Quartus itself, if you like, or from the desktop as you prefer, the simulator. But perhaps you can see if everything is all right, running the timing diagram, right? Which is going to tell you the information of the worst case condition. So you click the timing analyzer and the machine runs this device. Okay. And it looks like that is in red. So perhaps you have a problem here. Let's see what happens. What kind of the timing analyzer tool is like this one. So let's see if we can inspect as a report the data sheet. All right. And then in the timing analyzer we can see data. If possible, you see it's not generated the data, so we have a problem here. Not slow model or fast model available. And no calculations of frequencies or anything similar. No. So we have to go back. You see, there is no need to run the simulation. I mean, there is no need to run the gate level simulation later on because the timing analyzer is not really very well solved. So the EDA tool writer is not going to work the same, right? So, well, but we can wait for this for the next testing, because first of all, what we can solve very well is the functional simulation. So let's run that functional simulation first, this way. And when in the model sim window and platform, you start as usual a new project. So browse for the right location, that is that one, RS latch. That's the project location of interest. So the project name is RS latch functional simulation, functional sim, and the library is work functional, that way, as usual. So you say okay, and now it's time for adding to the project the two files of interest, the latch and the test bench, both of them. So now it's time to close this window and just see if everything is compiled correctly by the system. Everything is fine, successful, 0 errors. So now it's time to run the simulation. Let's start it and let's pick up the right entity to simulate. That is nothing but what you see here in work functional, but not the internal component, but the test bench. So let's click that one and say yes. So that now the waveform monitor is going to be here, just like that. So you can go to the entity, you see, to the instance, and you can very well say something like add to wave all items in design in the region. And that's the case. So you can add a divider output. So you can place the Q down there on RS, so it looks pretty much like the circuit that you have in paper. So now is your turn to run. For example, forward with that we set 200 microsecs, and this is the final result, and we zoom all, and this is the teeny waveforms that we have here, you see? So let's see what happens. Let's see if this is what we are expecting or not. You see, first of all, it was not defined. Then, you see, the undefinition continued. You have 0, 0, but you see, you carry on with you the undefined, unknown state of the output until you do something like this that is very clear. You say R equal 1, S equals 0, and the output is settled or reset. And then here you have 0, 0, and the value is kept. Then you have 1, 0, and immediately you see, with no time, you get a 1. You save a 1, the output, and this 1 is kept forever unless you are inputting another condition like this, save a 0, and then save a 1, and the like. And if it happens that you are 1, 1 in this simulator, you see the 0 value is kept. But in some way, when the situation clarifies, you see, when you have again a clear order, not something like this 1, 1 that is not predictable, but so when you have 0, 1, the output goes straight to 1. And that is the end result, even if you go to 0, 0 to the end. So that picture demonstrates that functionally the circuit that we have invented works very well. All right, that it can be used in some applications, not very much of them, but in some applications, for example, a circuit like this connected to push buttons and switches may help you to get rid of switch bounces that are something that is a big problem in digital systems. So we will do that not using latches perhaps, but using another idea, that is getting rid of switch bounces using a finite state machine in the next project P6. So that is in some way the end of the functional simulation. So now that the functional simulation has worked properly, let's go to the next step 5, and that means running the gate level simulation and the timing analyzer. The timing analyzer seems not going that well because, you know, perhaps the circuit is too simple. If you call, when it is in red, you see all the operations in the flow chart are in green, but you know the report of the timing analyzer looks like that in red. So this means that perhaps nothing is calculated this time because of the simplicity of the circuit, you see. I guess, I don't know, because, for example, if you try to do as usual, the operation of generating the report datasheet, you see, is nothing to explain. No fast model, no slow model, doesn't matter. So this time, the timing analyzer is not that useful, you see. It has no data, it seems so. So we can go to the gate level directly. And this means that we have to be sure that the EDA netlist writer is able to generate all the necessary files. The structure, that is the translation of the VHDL, is the translation of the technology view, and as well the standard delay file. So let's go to the assignments and click settings and see if this is what happens. You see EDA tool, settings, simulation, and here you are the possibility to see extra EDA netlist writer settings. You click and every one of them has to be off to do that. You see, to do that generation of the functional simulation netlist. Okay, so you say off to every single option. You say right, okay, and apply, and okay. And now it's time for perhaps recompiling it all and getting the EDA netlist writer files. So once the process of synthesis has finished, we will inspect the EDA netlist writer. This is the summary. It was successful. The family this time is a MAX2. The chip, the top level entity name is the RS latch. So now we can go to the simulation and keep an eye on the generated files. You see, it is the RS latch and the RS latch the VHD SDO. That two files are the ones required for the gate level simulation. So now it's time to go and run the processing of these files. The tool, run simulation tool, the RTL simulation. As you can see, the timing analyzer this time generates no rise and fall delays, no, you see, no maximum frequency summary or nothing like that. So it is not working this time for the circuit. But fortunately, we can go to the gate level simulation. And this is what we've got here. The idea of starting now a new project in the same folder to make it simple with a very similar name, okay. But now the project name is RS latch gate level simulation, and the library is work gate level, that way. So you say okay, and now is when you will add the files of interest. But remember, there is only one file of interest here in the root folder, and this is the test bench, because you add it that way, and then you add another one that is the structure, that the technology view structure. So you can browse to the simulation model sim, and that rs/pho is the structure. So you say okay, and that file as well is added to the project, and now you have it. You have the test bench fixture completed. The test bench that has no ports, okay, and the VHO, that is the device and the test. So you can compile them both, no errors, you see. And this is what we have to simulate now. All right, if you like, you can keep an eye on the VHO. It is like this. You see a file that now has extra libraries to define the chip very well, to model the chip very well. You see, you have this MAX2 library because it belongs to the, you see, it is the target chip. And then you have the entity, okay, the RS latch as usual, okay, and then the architecture. But you see what has happened here? You have many signals and different kind of gates. So this flat circuit is the one that we will simulate just now. So let's do that, okay? This way, simulate, start simulation of what exactly? Well, let's pay attention here, because this is where sometimes it fails. You have to click on the gate level now and select the top entity. You may name it, like you can copy it. No, let's name it like this, RS latch, right? So this is the name of the top level entity. So RS latch, and then the standard delay file may be added here as well from the simulation file folder. This is the RS latch SDO. So you attach that, but to this entity, the RS latch VHD TST, remember the one that has no ports. And now you can add here /I1, because you see that's the name given when instantiating in this plan situ, if you like, schematic, the component and the test. That's the name given, not chip 1 as we do all the time when we have to write these kind of files. But this is the name given by default by Intel. So you say okay, and now you say okay. in the previous simulation, we have already solved the structure of the waveforms. So you can load the macro file, wavedo, to make it simple, and the same as in the previous example if you like, and now you can start running this. Okay, run for 400 microseconds, and that's the final result. Pretty much the same, you see? It works as before, no problems, but this time you see when the input is set high, you can go zooming to this transition in order to reach, you see, the nanosecond scale. This is, you see, it doesn't look like that, you see, in the full range of the view you have a perfect match. The input changes now and the output changes the same to 1, but now if you zoom this way, you will see the delays associated to this transition. This is when you are giving the order of saving a 1, you see? This is where it happens. And now you add another, you see, another cursor, time cursor, and places it when the output really goes high, so that you have a time of 5.52 nanoseconds in between. That is the transition time from the set input to the output Q. Basically 2 gates, okay? 1 gate changes and then the next, and then the output is settled. So that is the propagation time of the circuit. So that is the perfect solution of this exercise, okay? It worked fine, so you can do that and repeat as many times as you like. Now, it's time for copying this picture, this wave, into make a screen copy and add comments so that it looks like what we have in the demonstration web page. This is what I mean, you see? The testing functional and the results from the functional testing, and now the timing, the gate level testing, and this is what we have here. For example, here the time is 5:52 and here 6.36, but that depends on that depends very much on the complex PLD or FPGA that you are using as a target chip. So this propagation time is giving you an idea of how fast can you go running orders of saving a 1 and saving a 0 in this simple latch.